All right, good morning, everyone. So we're going to continue our discussion of training methods and after that, transfer learning. But before we get started, I just wanted to remind you guys that in 1 week from today, next Friday, you have a midterm, your second midterm. So that will cover units 5 through 8. So classification, optimization, support vector machines, and the 2-layer neural networks. So this stuff, Unit 9, will not be included on that midterm. So I'm planning to have it here in the classroom. You can bring in 2 note sheets, so you can bring in your note sheet from last time, and you can make another one of equal length, so 1 page, double-sided. And next week, I'll have a day where I'll do the review, and then I'll post practice midterm, hopefully today, so you can get started on that. Any other questions? Okay, so it should be pretty similar in style to the last midterm. Yes?
Don't we have like homework?
So next week, so your homework for Unit 8 is due this Friday, right? And so that will cover all the material for the midterm. Next week, because of the midterm, we will not have homework or lab due. So you can focus on the midterm next week. Unit 9 will be due 2 weeks from today. Okay, great. So back to the lecture material. So we were talking about training. So we talked about how to do back propagation, forward pass, backwards pass. We talked about the advantages of GPUs. Talked about the importance of learning rate and how it's different from convex optimization and how we might want to schedule it. And now we'll move on to the next topic, which is called batch normalization. So this is a way to speed up training significantly. And the way to think about it is to remember standardization, which is something we talked about for a long time. So when we standardize, what we do is we make our mean 0 and our variance 1. And typically this is something we want to do at the input to some prediction algorithm, whether it's, logistic regression or a neural network or whatever. That's always a good thing to do. So the idea behind batch normalization is to actually redo that at every layer within the network, so that when you go into the next layer, things are properly normalized. Okay, but it goes a little bit farther than that even. So in particular, what we do is you first standardize the linear outputs in each channel and in each layer separately. And then, once they're standardized, you learn an optimal mean and variance that you learn a new shift and a new scale after it's standardized. And so if there's something better than using 0 mean and unit variance, you can learn it and you can do it. So that's basically the idea. So the equations would then be to compute the sample mean. Now notice this is the sample mean for layer L and for channel M. So for each layer and each channel, we compute a separate sample mean. But when we do this mean, we're taking the mean over all the images in the mini batch, as well as all the pixels in each image. Okay, so basically, otherwise it's just averaging the linear scores that come out of the linear layer. Once we have those averages, we just subtract them, to make something 0 mean. And then the next thing is to estimate the variance. So as we know, to estimate the variance, this is essentially the sample variance estimate. You subtract the mean, you square it, and we do another average. Again, averaging over the images in the batch and the pixels in each image. The square root is used to convert that variance to a standard deviation. Eventually, what we're going to do here is we're going to subtract the mean and divide by the standard deviation. So this is the standardization. But as you can see, we have a big problem if for some reason this value goes to 0, right? Because then this whole thing goes to infinity. So to prevent that from ever going to 0, this is a common trick, is you add a very small positive number here, so that the smallest this can be is square root epsilon. Even if this all goes to 0, this is square root epsilon. So you choose this as a very small number that in most cases it's much smaller than this, so you don't see the effect. But if this gets really small, this is there to save you. Okay, so this is, so this part here is the standardization. And then this new part, learn an optimal mean and variance, is done here. So once we have standardized, now we can learn 2 parameters, another shift and a scale. This would be the new mean, and this will be the basically the new standard deviation. And then that's what we put out to go to the activation, which comes next. Okay, so does that make sense, what we're doing? So again, it's like the main idea is standardize the linear outputs in each channel and layer. The intuition behind that is the same as always. When you make things, sometimes if things are too big or too small, the prediction doesn't turn out well for various reasons. So this just makes everything a good size before every layer.
I thought that we were applying the activation function to make sure that the outputs weren't too large.
So the activation, like if you think about an activation like ReLU, this just goes, so like, the positive input, the positive things are not touched at all. So if they're really big, then the outputs of the activation are really big. So the activation won't really do what we're trying to do here. We're trying to make sure that quantities are normalized so that when I look at different channels, things are about the same size, and when I look at different layers, things are about the same size. So this is, again, in each channel and layer, we're doing this normalization. Now, there is a debate about whether you should do this normalization on the linear outputs or on the activations that come next. The original paper proposed to do it on the linear outputs, but if you read about it online, you can find that most people say you should probably be doing this to the activations because at least if you just think about this standardization part, if you standardize Z and then you go through the activation, it will no longer be zero mean and unit variance, right? Because the activation will change all that. Now you could say, well, I'm not actually making it zero mean and unit variance because what I'm eventually doing is I'm eventually learning a shift in scale. And I'm learning that shift in scale before the activation, but it will have whatever effect I want after the activation. So in the end, it doesn't make a huge difference whether you put it before or after the activation if you're learning these parameters. But there is a debate about whether it should come before or after. I don't think it matters that much, and based on the experiments I've done, it doesn't matter that much. Okay. All right, so any questions on what we're doing here? Yeah.
One more. Are those parameters hyperparameters, or are those learned from gradient descent?
These are actually learned with backpropagation. Yeah. Yeah, exactly. These are learned with backpropagation. So because there's going to be a lot of them, remember like the number of channels in the second layer of AlexNet is like 96. So that would be like 96 times 2 parameters right there. That's not something that a human could adjust by trial and error. That's something we need a machine to adjust. Okay. Yes?
Why batch normalization can speed up training?
Yeah, okay, let's talk about that a little bit. So, here are the things that it accomplishes. So the main intuition, I would say, is that it reduces variation across channels and mini batches. So if you don't have batch norm, what can happen is when you look at like a given channel and a given batch, sometimes it can be very large, sometimes it can be very small. And when you have that kind of uncertainty, it's hard to, the next stage has a hard time dealing with it. It's like when you think about choosing the learning rate in an algorithm, you know, if the gradient is very shallow, you want to increase the learning rate. If the gradient is very steep, you want to decrease the learning rate. But if the gradient is constantly changing, it's hard to find a good value that works for all cases. So by making things uniform, it helps a lot. And so another effect of this too, it's a little bit harder to see, is that it helps to decouple the layers from each other. And what we mean is that what happens in one layer does not have such a huge effect on what happens in the other layer because of this normalization. And same thing with channels. It decouples the channels as well. And though it's difficult to see, there's a paper, if you click on this green link, that did an analysis and was able to show that it makes the cost function smoother, actually. And the smoother the cost function is, the easier it is to optimize. So, yeah, the original paper has a kind of weird explanation for why batch norm works, and then there's been a number of follow-on papers that have tried to clarify with better explanations about why batch norm works. But it's not something that I think there's like a very easy explanation to understand beyond the intuition that let's just try to make everything sort of uniform so that there's no surprises, and then that makes things easier to deal with. But here's a nice experiment that shows the effects, and this is from the original paper. So just as a reference, we have, this is, we're going to talk about this network later today. This is a Inception network. And this is, the dashed line is without any batch norm. And you can see, I think this is going to be accuracy on ImageNet. And after 30 million, this is probably not 30 million epochs, it's probably like 30 million batches. It gets up to, I don't know, maybe like 72, 73%. When we add batch norm, we get this red dashed line. And as you can see, instead of like 33 million, it's now maybe like 13 million batches. So it's sped things up a lot. However, it's not, we can even do better. Batch norm actually allows us to use a more aggressive step size. So we can multiply the step size by 5. And when we do that, we get this dotted line over here. And now you can see it's way faster than before. Huge speed up. And just to try it, they said, what if we increase the learning rate by a factor of 30, which is really, it's bigger than you want, but let's just see what happens. The network still does quite well. And in fact, I mean, it's maybe not quite as fast, but as you can see, it gets, you know, to a better performance. And then they did an interesting experiment where they said, well, you know, we always use ReLUs in deep networks because of the vanishing gradient problem, so everyone knows you should never use a sigmoid. And if you tried a sigmoid with regular inception, it wouldn't work at all. But with batch norm, that makes it, you know, that has such a great effect that we can actually put in a sigmoid and we can still train the network to a reasonable performance. It's not, you know, maybe it's like 68%. It's not as good as this or as good as these, but it's you can see that it still pretty much works. Okay, so all these experiments are showing the positive effect that batch norm can have. Since batch norm was proposed, there's been variations on this, which essentially just change what you average over. So maybe instead of averaging over the images in a batch, there's something called layer norm, where you average over all the channels, but then each image in the batch is treated separately. So it's like you're swapping the M and I indices here.
On the other slide, it's interesting that the BNX30 has the highest accuracy with such a large learning rate. Is there any explanation for?
Yeah, I guess, well, maybe I said it wrong before. I mean, maybe for this problem, even though it's not the fastest converging over here, it eventually does converge to the best error rate. And so this might just be an example that sometimes when we use a larger learning rate, we can escape this bad local minimum. We can get into a better global minimum. And so I think that's probably what's happening. Yeah. All right, so that's batch norm. Any questions on batch norm? Okay. Let's talk about another technique called dropout. So dropout is a technique that can help reduce overfitting. And it might sound a little crazy, but essentially what you do is you temporarily remove a random subset of neurons in each mini batch. So, in other words, if this picture shows what happens after you go through 3 layers, so this is like the inputs, and then you go through, one layer, you go through a linear layer, and then some activations, and then you get another set of neurons or features, another layer, and so on. The idea behind dropout would be you basically just get rid of a number of these neurons completely. And so now you have a sparsely connected network. So you don't compute these at all, you don't use them. This one is computed only from those ones in that mini batch. In the next mini batch, you choose a different random subset of neurons to throw out. So you're constantly almost damaging your network by taking out a big part of it, but the part you change is random. So it's like and you only do this during training. So during training, it's like you're giving your network, you're making it have a really hard time. But then during testing, you let it have all the neurons back. And now it can perform a lot better. So in terms of intuitions about why this works, I think the one that makes most sense to me is that you're actually training an ensemble or a collection of simpler networks. So we'll study this in the next unit, but the idea behind ensemble methods is you have a bunch of relatively weak learners, weak predictors. On their own, they're not very good, but if you combine them in the right way and somehow average their outputs, they can do very well. So this is the concept behind ensembles. And we'll spend a whole unit on this, but here you can think of this as one weak learner in your ensemble, and you have many other ones that look like variations of this, and you train each one of those, but then finally during the test time, you put them all together. Essentially by doing this, it's kind of like you're averaging all of these. And then finally you can have a much better output. So that's kind of the intuition, and we'll see that yes, it does work. So here's a little bit about the details about how you implement it. So first of all, this dropout stuff is typically used before dense layers only, not convolutional layers. because convolutional layers have a very particular structure, and if you take out random subsets of pixels, it just doesn't really work well anymore. So this is something to be done before dense layers. Okay, so the way that you take out nodes is that you multiply them. You multiply each node by a Bernoulli random variable. So this is a random variable that takes one of two possible outputs. One of them we're going to call, so these are the activations. We're going to multiply these by a variable d, and d will either be 0 if we want to drop out, or 1 over p. And p is the on probability, the probability that it's not equal to 0. So let me give you an example. Let's say I have the on probability of 0.1. So 10% of the time I turn on the neuron, and 90% of the time I kill it. So in that 10% of the time that I turn it on, rather than weighting it by 1, I actually weight it by 10. So that on average, the value is 1. 90% of the time it's 0, 10% of the time it's a 10, so on average it's 1. So this kind of compensates for the fact that when a neuron is not on, so whenever the neuron is on, it's on in a kind of a loud way to make up for the times when it's not on. So this is the standard implementation. The value that you use for P, the on probability, this is a tuning parameter. So I think by default people use 50%, but this is a hyperparameter that you can try different values on. Maybe you want to use 25%, maybe 75%. You can try different things. So this is, the idea here is you either 0 the activation or you scale it by 1 over p to preserve the average value. Okay. And again, this is only done during training. During testing, you use the full network.
And is the P specific for each neuron? Can you use the same P for the entire network? Or?
You use it for each layer differently. So you could use a different value for each layer. It's more things to choose. So maybe it's just easier to use one. Okay, so here are a few things to watch out for. So when you do this, it actually takes longer to train because you're giving the network a hard time during training. You're taking out a big random piece of it every time. So it's having a harder time, and it takes longer to train. That's just how it goes. Also, because you're taking out a big chunk of the network is actually weaker. So it reduces the capacity. So you might actually need to increase the size, maybe, maybe not. So again, what it's doing, the main thing it's doing is it's reducing overfitting. So if you see that the network is too powerful, that means if it's overfitting, you can use dropout to make the network less powerful. On the other hand, if the network is not overfitting and you want to use dropout, then you should probably make the network more complicated so that it is overfitting so that you can do this stuff. Because otherwise it will be too weak. Okay. And like I said, it's not standard to do this before convolutional layers, but people have proposed versions of it that work better for convolutional layers, but I don't think they're used very often. In fact, dropout as a whole is something that is not used as often now as it was a few years ago. It was very popular, and then now it seems like the field has moved away from it. Still, if you use kind of basic networks, you will see advantages, as I'll show you an example. Okay, so questions on dropout? Yeah.
So because you're testing with like a different set of neurons than you're training with, would that ever cause a problem, or does the averaging always like fix that?
Yeah. Again, so you're using a different average set every mini batch, and you've seen like thousands of mini batches. So I think that averaging over all those thousands of different configurations kind of works out that when you do this, yeah, see the average. If you were doing this for the same pattern, you know, every mini batch and then you did this during testing, yeah, it wouldn't work. But it's the randomness. It's okay.
I don't understand why they're using 1 divided by p, because like 1 divided by 0.5 would be 2, so that they get larger. But I would assume you'd want to make it smaller.
So I think, yeah, you're right, exactly. So what we're saying is like when the neuron is off, you're putting out 0. But when the same neuron is on, you're going to put out, if it's on half the time, you're going to put out twice as much, so that on average, what's coming out of that neuron is the same. Because otherwise what happens is the average size of the outputs just decreases the more dropout you do. And then I think it won't work when you finally put things together at the end. So you want to compensate with this 1 over p. It's preserving the average value. All right. Okay. Any questions on dropout? All right. Okay. Another very important thing that is done a lot is called data augmentation. The idea is we always want more training data than we have. Even if we have a lot, we wish we could have more. So one way to get more is to fake it. Basically, you take what you have and you try to make it look different. And if we're talking about images, we can do things like flipping. That would be a horizontal flip left to right. We could shift the image, we could scale it, we could rotate it a little bit, we could crop it. And when you do that to images, this is an example of, okay, this is, let's say, the original image. And then if I zoom into, I don't know, maybe I'm zooming into here, that's this next image. And if I zoom into here, that's this image over here. You can see it looks like I've made 3 different images out of the first one. So it really depends, what kind of transformations you can do kind of depends on the data you're working with. So like for images, you probably don't want to flip it up, down, because in a lot of our images, there's a sky above and ground below, and if you flip it vertically, it actually doesn't make any more sense. And so that's something you wouldn't want to do. But most of our images are symmetric, not symmetric, but we can flip them left to right, and when you look at it, it still makes sense. Of course, that wouldn't make sense if you were working with MNIST, right? Because MNIST, we can't flip a digit left to right, it's different then. So there's exceptions. You just have to think about your data set. What kind of things can you do without really changing the meaning, the semantics of the data? So for natural images, flips, shifts, scales. Another one I didn't talk about here is color changes. If you have color images, you could, like if I show you a picture of a cat and then I change the colors and I show you another picture, even if the cat is purple now, you can still tell it's a cat. Right? So that kind of color, they call it color jittering. That stuff is usually okay. Rotating to a certain extent, 90-degree rotations, probably not a good idea, right? Because all of a sudden the ground is like up, down, but crops are fine. Okay, so basically that's the idea. So you can make your data set bigger than it is. And if you look at the implementation in PyTorch, the place that you do this is you do this in the data loader. And the data loader has all these standard augmentations that are available for you to select if you want, and you just tell the data loader which augmentations you want to do. So it's made pretty easy. And there's a tutorial about how to do that here, if you want to take a look at it. Okay, so that's data augmentation. Any questions? All right. So what about activations? So we said, I think maybe earlier in this unit, we said the ReLU is a really good activation to use for deep networks, because if you try to use something like a sigmoid or a tan-H activation that's like this, the gradient is only significant near the center, and when you get to the outsides, the gradient is near 0. And if you back propagate through many of these guys, eventually your gradients get smaller and smaller and smaller until they vanish by the time you get to the beginning of the network. And the problem becomes worse the deeper the network is. So that's why ReLU is great, because the gradient on this side is 1, and it never decreases. But there is a problem with these. So the gradient over here, the values and everything are 0. So what can happen sometimes is you find that after you're done training, there's a subset of nodes in your network that are just stuck outputting 0 always. And if they're outputting 0 always, let's say for all the training data, then they're essentially not doing anything good for you. And you could say that this is just an example of falling into some bad local minimum where somehow we're not getting to use a subset of our neurons. So one good way to prevent that without changing too much is you just add a slight slope to the negative side. Use a slope of, let's say, 0.01. So like you can barely even see it when you look at this picture, right? It looks pretty much the same as this, but actually there's a tiny slope here. And the fact that there's a tiny slope here means that 0 condition doesn't really exist anymore. So it's impossible to get into this dead ReLU situation anymore. But still it acts more or less like a ReLU. And there's even this is the leaky ReLU. There's even a more sophisticated version of this that says, let's make that left slope learnable, parametric ReLU. So you can learn that. Maybe you'll find something that's better than 0.01. Okay, so this works pretty well. And there's many, many other activations that have been proposed. So one of them that seems to work relatively well is what's called the exponential linear unit. So this guy on the positive side looks exactly like a ReLU. So it has this slope here. But on the negative slide, instead of being a line like these guys, it has, as you can see, it's curved here, and then it almost flattens out, but doesn't perfectly flatten out. So the equation is this. Okay, so as you know, when z becomes a large negative number, this gets closer and closer to 0, after which, once this is exactly at 0, then this would be a slope of minus alpha. So it would be So basically, well, let's see. So this, okay, so let's see what happens when when z is 0, the value of this is exactly 0, right? So that's why this minus 1 is here, because we want that when this has to be continuous. So when z is 0, this has to match this. So they have to agree at that point. And then the rest of this is set up so that as z gets more and more negative, this gets smaller and smaller. Okay, and then it sort of straightens out. Gets something like that. So yeah, so as you can see, I think I said it wrong. So the final value that this approaches is it approaches negative alpha. So alpha is some positive number. and the final slope that it approaches is 0. You know, as a function of z, basically it flattens out. But the value is so by default 1. Okay. So one advantage of this is that this is smooth, and when you do optimization, it's much easier to optimize smooth things than it is things with non-smooth things with discontinuous gradients. So that could be one advantage to this. There's some other explanations in terms of bias shift if you want to read more about it. Sometimes those explanations are kind of made up. They don't always, it's just somebody's opinion about what might be going on. Okay, so that's activations, and like I said, there's many other ones you can use as well.
Yeah.
All right, any questions on, yes?
I think also the other property is the complexity, right? For the exponential, the ELE.
Is the what?
Complexity.
Well, yeah, I mean, I guess, this particular shape is convex, but that doesn't make the network as a whole convex.
Yes.
So I don't know that the convexity of this is necessarily helping. To my understanding, it's nonlinear, which is essential. It's smooth, which is helpful. It has this slope of 1, so no vanishing gradients. All that's great. So I think probably what's happening relative to these is smoothness might help in some situations. Okay. All right, any other questions on activations? All right. Okay, so let's look at a demonstration. There's 4 different demos in this unit. So this is in demo B. And in this demo, our goal is to classify CIFR 10. So if you remember CIFR 10, I showed a picture near the beginning of these slides. This is a data set that has 10 classes of images, and the images are small. They're 32 by 32 in color. And so we want to train a relatively simple convolutional neural network. We're going to use 2 convolutional layers, each with ReLU and max pooling, followed by 2 dense layers at the end. So on the left here, we have the training accuracy, and on the right, we have the validation accuracy. And this is versus number of epochs, so up to 100. And so when we look at the baseline network, that's the blue one, you can see that the training quickly goes up and eventually gets pretty much up to 100%. Of course, that doesn't necessarily mean that your test error is going to be, your test accuracy is 100%. So when we look at the test accuracy, it goes up quickly, but then it sort of saturates in, somewhere maybe around 67%. So you can see there's a big difference between training and test. So this network is overfitted. Okay, so one thing we could do is we could add batch norm. So then we're going to have this orange trace. I can't remember if the step size, the learning rate has changed or not. I'm guessing it's not changed. But what we see is the training accuracy is similar. It's not really any better. But what's more important is the validation accuracy. And here you can see this got us an improvement of like 5%. So that's pretty significant. So now what if I add dropout? So when I add dropout, on the training accuracy, it looks like things have gotten a lot worse, right? Huge drop. However, look what happened in the validation accuracy. Huge improvement. So this is an example where you had a network that was overfitting, and then you said, let's give this network a hard time while training. I'm going to take out all these random subsets of neurons. Now it has a hard time with the training, but when you put them all back together for test, it actually does much better. And the last thing we can try to do is data augmentation. Now somehow, in this example, it didn't really help us. Okay, so this got a bit worse. Validation accuracy is pretty similar. You can see it's a little bit lower, but it's catching up. Maybe if we let it run longer, it would catch up. So exactly why this didn't help, not sure. Maybe we have enough data for the complexity of the problem, or maybe we could have done a little bit of more tuning of the parameters, and maybe eventually we could have made the data augmentation work better. That's sort of my guess, but from what I remember how the demo goes, it's just simply adding the data augmentation and using the same parameters. So, but it's an example of how to do all these things. You can take a look at this, and you'll get a chance to play with some of these ideas also in the lab. And there's many other good demos. There's another one. If you want to click here, you can find one. Okay, so any questions so far? All right, so we're getting close to the end here. Not quite at the end yet. So the next thing to talk about is an idea called transfer learning. And the main idea behind transfer learning is that these state-of-the-art networks that we've been talking about, they take enormous resources to train. So they have millions of parameters, and that means we need to use, let's say millions of images, and that means days or weeks of training on these GPU clusters. So it's not the sort of thing that individuals like you or I can really just do on our home computers. However, we can often take the work that Google or Microsoft or whoever did for us, and we can exploit it by essentially taking a pre-trained network and then just changing a little bit about it to adapt it to a new task. So that's the main idea. And the way this works is that the early layers in these convolutional networks are more or less universal. So let's say I have a network trained with ImageNet, and I want to use this ImageNet network. I want to apply this to some new images that are not in ImageNet that maybe I have collected, for some project I'm working on. So all the early layers for ImageNet, trained on ImageNet, will actually work great. It's just the last ones that I need to change. So I'm going to keep those fixed, and I'm going to retrain the later ones, like the dense layers, to perform well on a new task. Now the idea now is if I just have 1, 2, or 3 dense layers, something like that, that's not that many parameters to train. And in fact, I can even change the size of those dense layers if I need to. I can make them smaller if they're too big for ImageNet. Because ImageNet has 1,000 classes. If I just have 2 classes, I don't need maybe as big dense layers. But I can keep all those early convolutional layers pre-trained at the ImageNet values. So that's the idea. And so because typically this data set I've collected, it's not so big, but it's enough to train just a few layers, but not the whole network. So it works out. So that's what you'll do in the lab, is you'll go and you'll get images from Flickr, the photo site. You can just download, you can type in a keyword like bicycles, and you can download as many bicycle images as you want. There's probably, definitely thousands of them there. And then you could do like bicycles versus cars. Download cars, and then all you have to do is train those last layers on your data set that you collected, and it will work pretty well. So that's the idea. Any questions on that? All right, so now in terms of these pre-trained nets, there's actually many to choose from. So that's what we're going to do next, is we're going to talk a bit about the evolution of deep networks over the years, the trends, and some of the more famous ones. Like I'm going to cover most of the ones that are in PyTorch. PyTorch has added a few more to this list, but we'll talk about the ones on this list. And then we'll go through a demo to see how this is done. Okay, so remember that the very first really kind of breakthrough network was AlexNet. We talked a lot about AlexNet so far. So this is sort of the next big thing. I think this is the next year after AlexNet. So this would be, or maybe 2 years, something like that. This is basically 2014. It's, once again, it's that image, the visual recognition challenge, that same competition that was held for several years. So what are the main ideas behind what changed in VGG? Okay, one of the main ideas is they figured out that it's better to use many small kernels and more layers. So remember that in AlexNet, the very first kernel was 11 by 11. So they realized it's actually much better to use 5 convolutional layers of 3 by 3. And the reason we can compare these is that the receptive field is the same for both. So by receptive field, I mean, if I have one 11 by 11 kernel, the receptive field is 11 by 11. So one output pixel responds to 11 by 11 pixels in that patch, right? But if I have gone through 5 layers of 3 by 3 kernels, so the first layer, I see a 3 by 3, but then the second layer, I see 3 of the first, right? I basically, every time I do a convolution with a 3 by 3, and then I do another convolution, another, the patch gets bigger. So essentially, if I do 2 3 by 3s, I get a 5 by 5. If I do another one, I get a 7 by 7. Another one, I get a 9 by 9. And one more, I get a 11 by 11. Does that making sense? It's just like convolving a 3 by 3 with another 3 by 3 and another 3 by 3. It gets effectively a bigger and bigger kernel. But the key thing to remember is that when we do this in a deep network, not only do we do the convolution, but we will also do a nonlinear, like a ReLU, after that. So really the comparison is one layer of convolution ReLU with 5 layers of convolution ReLU. So 5 nonlinear layers versus 1 nonlinear layer. And with those 5 nonlinear layers, that's much more powerful than one of these nonlinear layers, because those nonlinearities can really do sophisticated stuff. So that's the main idea. That was one of the big things they figured out, is that the kernels in AlexNet were way too big. They should use small kernels and a lot more of them. So the network is getting deeper. The kernels are getting smaller, so less parameters to train per layer, but more layers. So this network, you can find pre-trained versions at various lengths, 11 layers, 13 layers, 16, 19. I think they're all pretty good. The 16 layer one, I think this one, or maybe a few of them won some of the contests. But if you look at this one, the top 5 error rate was 7.5% compared to AlexNet, which is 15.3. So it's basically halving the error at AlexNet. So it's a big step forward. And this is what it looks like. So we start with our color image. Then this black one is convolution and ReLU. We do actually 2 layers of convolution ReLU, 64 channels each. And then we do a max pooling that changes the size down to 112 by 112. Then we do 2 more convolutional layers, grow the channels to 128. Another max pool to get us down to 56 by 56. Then 3 more layers of convolution, 256 channels. Another max pool down to 28 by 28. Now we grow our channels to 512, 3 more layers. Another max pool down to 14 by 14. 3 more layers still at 512. Finally, 1 more max pool down to 7 by 7. And then we flatten. And after we flatten, we go through our dense layers of 4096. Looks like we have 2 of them. And finally, when we're done, we get down to our 1,000 layers that we need for the ImageNet competition. Okay, so that's the structure of the network. And even today, this is a pretty good network in terms of like you can use the lower layers as a good feature extractor for other vision tasks. So maybe like you use this part to generate these 7 by 7 by 512 vectors, and then you use them for other things. It doesn't have to be image classification. It could be various other things. But you could also use it for image classification. You just need to train this stuff on your data set. So one thing to keep in mind is that this has about 3 times the number of parameters in AlexNet, so it got bigger.
When you're doing the transfer learning, and you like take the convolutional network, the convolutional part, and it's just acting as a feature extractor,
Mm-hmm.
then are we still limited to only using a neural network as the classifier, or is the classifier not matter?
So you still, so the traditional thing is still to use exactly this for your classifier. So this is still like, 3 layers. So this is, you could say it's kind of like a dense neural network. So these are your features that you extracted, and then this is the part that you retrain. So these you're using the weights that they trained, and then these are your own weights. I guess you could try taking out layers here, but use at your own risk. So might not work as well. Okay, all right, any questions on VGG? All right, let's talk about the next evolution. So if you look at what was happening, performance was getting better in these contests. Basically, the networks were getting deeper. But at the same time, they were getting bigger, more parameters. So AlexNet had 60 million. By the time we got to VGG 16, we had 180 million parameters. This is sort of stressing the limits of what could be handled, especially at the time. So they saw that they wanted to make things deeper, but you can't just continue with the same architecture making it deeper because the number of parameters would get too large. So they had to rethink how they were doing the network. So essentially they wanted to design a network that was deeper but more efficient. And there was a film called Inception at the time that they kind of played on the name. In the film they talked about, I actually haven't seen the film, but in the film they talked about needing to go deeper, and so these guys called their network Inception. And they came up with a network that used only 5 million parameters, right? Compared to 180, that's a huge reduction. But it performed even better than VGG 16. Not a huge amount better, but a little bit better. So this was really an advance in a much more efficient architecture. Okay, so how did they do this? There's various tricks they used, but one of the biggest ideas were these things called Inception Modules. And you can see it's pretty deep. There's 22 layers. So it's getting deeper, but it's more lightweight. So what are these Inception Modules? So you can think of it as several convolution layers in parallel with different kernel sizes. So it kind of goes like this. Imagine these are the inputs to your convolution layer. And now you actually have 4 of them. You do a 1x1 convolution, you do a 3x3 convolution, a 5x5, and another 3x3. For each one of these, you can choose how many channels you want. And then you concatenate all those different channels into this new feature map. So, and in particular, for bigger kernels, you want to use fewer channels, right? Because the intuition is if I have a bigger kernel, that's more coefficients to learn. And the total number of coefficients to learn scales linearly with the channels. So if I have a bigger kernel, use less channels. If I have a smaller kernel, I can afford to use more channels. So that's essentially what they did. So as you can see here, like the biggest kernel in this picture, 5 by 5, is using the smallest number of channels. And the smallest one, which is a 1 by 1, is using the largest number of channels. And so they just concatenate this all together, and then this goes through the next layer and so on. So these are these Inception modules. And there's other arguments for using different sizes of kernels. In some sense, there's sometimes when you want to look for patterns that are larger patterns, and sometimes you want to look for smaller patterns. And this is basically by looking at larger and smaller patterns, you can deal with changes in image size better. So maybe if I scale down an image, then maybe the cat I'm looking for is just a lot smaller now. So I should use a smaller kernel to look for those features. So by using different sizes of kernels, you can automatically handle things at different scales. And there's a nice overview that gets into more details here. So there was a few other tricks that they used, but that was one of the main ones.
Is the order in which you arrange the outputs of the different convolutions also variable? Or
I don't think it matters because the next layer will just learn to deal with those. Okay, so there's more to talk about. We're out of time for today, but we'll talk about residual networks and some other ones. And to try to kind of understand the evolution of these networks over time. But yeah, I think we're out of time for today. Are there any last questions on anything? Yes.
On the image where you had the dropout and the pulling where you showed the error was changing, right there.
Wait.
On this page?
Yeah.
Is this changing the bias or the variance of the time?
So you're asking if dropout is changing the bias or variance?
Like, how does this fit into the bias variance?
Yeah, okay, that's a great question. So because I'm making my network simpler, the bias is going to increase, right? Because if I have a super powerful network, it can do everything. So it can always match your model. But as I constrain my network, I introduce more bias. When I do my averaging, if you think about when I do the test, kind of like I'm averaging the ensembles, all these different simpler networks, in that averaging, that's where we reduce the variance. So you could say that we're increasing the bias, decreasing the variance when we do dropout. And yeah, in doing so, that's how we reduce overfitting. Because overfitting would mean you're on the side of too little bias, too high variance, or let's say just too high variance.
here we are reducing variance by
Yeah, we're reducing variance by the averaging. So if I look at this network, because I've turned off so many nodes, it's gotten weaker. So it's not as good at matching the true model. So I've increased the bias.
Yes, but I mean, there are this is mini batch actually. So we are taking the average of these mini batches, and then we have mini batch gradient. Yeah. But there are some other ways variance reduced methods that are saying that even this mini batch has again some variance that we can reduce it.
So, but we're not talking about mini batches anymore. We're talking about what happens during test time. So during test time, there's no more mini batches, right?
Oh, okay. But
Right.
while training the network, so we take mini batches.
We always do, yes. We always use mini batches in training. So to understand the effect of dropout, we should think, what are we doing different with dropout than usual. So the different thing we're doing is we're basically zeroing these nodes. We're turning them off. We're constraining our network in many different random ways, but it's always constrained. So the bias is always higher. But if I think about these as individual networks that get averaged when I test, then that averaging helps to reduce variance. Okay, good question. All right, any other questions? Okay, we'll see you guys on Monday.